Hi! In this video tutorial I'm gonna show you how to quick start with FCPP, a library for the execution and simulation of distributed aggregate systems. The first place where to start is the project webpage, fcpp.github.io, which contains general information about the library, some bibliographic references to related papers, and most importantly, instructions on how to get started using the tool. First, a foundational approach offers few selected papers and an introductory video course. Then, an alternative hands-on method allows to approach the library by solving some exercises of increasing complexity. The exercises project on GitHub contains minimal source files using FCPP that are ready to be executed, instructions to set up, build and run the simulations, a description of the repository contents, and the presentation of the main concepts needed to use the library. In addition to that, a link to an online automatically generated API documentation is also available, as well as a sample project containing a number of archetypal case studies ready to run. Let's try to go through the steps and see them at work. The first thing you need to do is install the necessary prerequisites, depending on your operating system, Windows, Linux or Mac. I have already done this, so I can now clone the repository. We click here to copy the link, and then move to a terminal window and paste the command. You can see that the repository has been downloaded. Actually, the FCPP submodule is still missing, but don't worry, the provided build script will automatically get it the first time we use it. The script is called make.sh, and without arguments it will print out its usage after downloading the missing parts. So let's run the spreading collection case study. We call make.sh, we specify GUI to enable the graphical user interface, then the command run, then we add the flag -big O to enable optimizations, and finally specify the name of the case study. Now we just wait compilation to end. The main interface window has popped up, while on the console we can still see some information about the resources used by the simulation, some warning and error messages, and a summary of the simulated network status, for instance the current time, the maximum distance experienced by the node, etc. As you can see, the simulation is currently still. Pressing a random key will most likely open the legenda of every available command. Let's make it bigger. Looking at it, you can see that we need to press P to start the simulation. Now the nodes are moving and they are also changing colors. The central color depends on their computed distance from the source star node, here. Their lateral colors depend on the estimated diameter. Let's navigate the window. As you can see, by hovering on a node, we can select it and have an access of the details information about it. For instance, we can see that this node has a speed of 25 and its shape is a sphere, etc. When we are done with the simulation, we can just quit by pressing Escape. Let's now see what are the files that allowed us to run our simulation. The files in the main folder of the sample project are configuration files for the build tools, and more details about them are included in the project README. The bin folder contains the executables compiled by CMake. The FCPP folder contains the library submodule. The lib folder contains most of the code of the case studies. We will see more about it. The output folder contains the textual output of simulation that was displayed in the console. The plot folder contains graphical plots produced at the end of simulation, if any are produced. And run contains some small launchers for the case studies. Finally, test contains some unit tests and the textures contain some images for the user interface. Let's first see the launcher for the scenario that we just saw in action. As you can see, it is pretty small and well documented. It mostly amounts to declaring a network type, network parameters, and then calling the run method. Two more launchers are available for the same scenario. One for a single textual run, and another performing batch runs in order to produce resuming plots. All of those three are based on a single header file in the lib folder, containing most of the actual code of the case study, called spreadingcollection.hpp. Here you can first see some simulation parameter. For instance, we could change the number of devices from 1000 to 300 and see what happens. You can see that the number of devices are changed. But let's go back to the code. After this, you can see some empty types, which FCPP uses as tags to annotate the data contained in each node. Then, the actual aggregate program follows. This function selects a single node to behave as a source and is used by the following function, along many functions in the CPP aggregate function library, such as rectangle walk, which makes node move within a rectangular area with a fixed speed. After the source is selected, the distance from the source is computed by another library function called abfDistance. Then, the maximum speed that any node experiences in the network is computed by a further library function, mpCollection. Finally, this maximum distance, which is a diameter estimate in the source, is broadcast from the source to the rest of the network to make this diameter estimate available everywhere. These values are used to regulate the node appearance. If we want to change that appearance, we can edit this code. For example, adding this line to highlight nodes that are within 50% of the diameter. Let's run the program again and see what happens. Indeed, some nodes are getting bigger. Alright, let's go back to the code one last time. This final part of the file consists of the simulator configuration, from the periodic sequence of rounds to the structure of the node data, and so on. All of them well documented. If, for instance, we want to change the initial device distribution from a square to a rectangle, we can go to this rectangle distribution and change this side by dividing by 2. You can see that the shape of the area has indeed changed. So, thank you for being still here. I think you're ready to go and experiment by yourself.